Hello, my name's Jordan J. Bird, and I'm here to present our work, Look and Listen, a multimodality late fusion approach to scene classification for autonomous machines. This is a publication from the Aston Robotics Vision and Intelligent Systems Lab, the ARVIS lab at Aston University in the United Kingdom. And we also collaborated with Cristiano Premebida from the University of Coimbra in Portugal. So before I get into summarising the project and going into more detail, I'd like to talk about the drive behind the project. And this is based on research that suggests that humans mainly use their temporal lobes and their occipital lobes to figure out their surroundings. So as the title suggests, we also look and listen, and then we perform an intelligent logical decision-making process to figure out which parts of that data we should use and what decision we should make. So there's an example here where the person asks, where am I? Well, I can see the trees and I can hear birds, and therefore I'm in the forest. And this multimodality logical decision-making approach allows us to reduce mistakes. So in this example, I can hear people and I can hear traffic, but I can see country fields, and therefore I'm in the countryside, because we make the logical decision that the sounds aren't as important as the images in this example. If we were to close our eyes and listen to the surroundings, we may make a mistake and say, okay, I think I'm in a city street or in a town. To summarise what we did, we tackled the environment recognition or scene classification problem, which answers the question, where am I? What are my surroundings? To do this, we collect a data set of videos from the real world. We classify the audio to the scene and the images to the scene, and then we fuse them together and see what happens if we classify them both to the scene at the same time. And we find that multimodality improves the recognition accuracy for this problem, and this also extends to totally unseen data too, that wasn't present during training. So why should we explore this? Well, autonomous machines are becoming more and more popular, which is inevitably going to lead to autonomous machines outdoors. So I'm sure we're going to see a lot more robots and drones out and about in the future. And so these are logical decisions that need to be made by machines without human input. And so here's the proposed approach. On the next slide, there's a larger image. But what we do is we process the videos into sets of images and audio, and then we also fuse the networks with a further layer before making a final decision. Here are the three neural networks. So this video clip has been split into images. The RGB is separated and we feed that into a VGG16 CNN before an interpretation layer is benchmarked. We then score this with a softmax layer and see how the classification performs. Again, we take the 1 second of audio from the video clip that accompanies that image. We extract the MFCCs for the second of audio, and then we perform an evolutionary search of MLP topology. That goes into a softmax layer and we see what that scores. And then finally, we perform late fusion where we remove the softmax layers from the two prior networks. We feed those final layer inputs into a dense interpretation layer, which is trainable. And then we perform a final prediction through softmax. So again, here we see the three neural networks, and these are the three that we're going to compare. Finally, after all this, because we find that multimodality outperforms the prior two networks, we take a look at some of the errors that were made by the two networks and see how maybe the idea of late fusion and multimodality can prevent those errors. To collect the data set, we collect data from 8 environments: the beach, a city, a forest, a jungle, a football match, a classroom, a restaurant, and a grocery store or supermarket. This provides a difficult classification problem because, of course, for example, a forest and a jungle tend to be very similar. At the beach, football match, classroom, restaurant, and supermarket, we hear a lot of human voices in the background, so they're quite difficult to discern from one another. So as I say, we collect data from these sources to provide a difficult classification problem. All of the videos are recorded from a first-person view. We balance the dataset by shortening the longest videos, which gives us 2,000 seconds per class. We have a totally balanced dataset. That is 33.3 minutes per class, which gives us a total of 4.4 hours of data to classify. We also collect 2 minutes per class from totally unseen videos to classify later on to see how robust the networks are. Here's an example of how we pre-process the data. So as I said before, from each 1 second of the video, we extract an image and the 1 second of audio to go with that image. We resize the images to 128 by 128 RGB matrices, and this is because the experiments were performed on consumer level hardware. It was a NVIDIA GTX 980 Ti, and this was around about the maximum that we could do for the images. The MFCCs are extracted from the audio at a 1/4 second window length, and then those 4 extractions are reshaped into a 1-dimensional vector. So we are classifying, at each step, we're classifying 1 second worth of data. For the audio classification network, because it's a relatively easy problem, of course we've got 4 MFCC windows, so it's quite an easy problem in terms of computational complexity. So rather than doing a linear search, we perform an evolutionary search of best network topology using the algorithm on the right. We run this 5 times. We allow a maximum of 5 hidden layers with 4096 neurons per layer, and this runs for 20 generations. Although we only report the first 10 generations, because by generation 7 all of the networks had stabilized and no more better results were found. In comparison, learning from the images is quite a computationally complex problem, so we can't perform an evolutionary search, unfortunately. So we benchmark following the CNN with a single hidden layer of neurons, 248 to 4096 neurons, and then we choose the best one. The multimodality is the same approach, 248 to 4096 neurons in a layer, following the late fusion, the concatenation layer, and we allow that interpretation layer to train. So that brings us on to the results. For the audio classification, there we can see the first 10 generations, which met stabilization for all 5 simulations. All the results were quite similar. The best result we found was a 4 hidden layer network, where the input goes to 977, 365, 703 and 41 neurons, and then to the output. This scored 93.72% accuracy. For the image classification, we found that the best network was the input to the CNN to 2048 neurons, then to the output, which scored 89.27% accuracy. Then for the multimodality, we find that the best result was the input networks to 32 neurons to the output, which scored 96.81% accuracy. And there on the right is a table comparing the CNN, which scored 89.27%, the MLP for the audio, which scored 93.72%, and finally fusion of the two to score 96.81% in a multimodality approach. So the multimodality for this problem was superior to the 2 prior networks. So why does multimodality perform better? Well, here are 2 prominent examples of errors that occurred. On the left there, in the first frame, the image classification network says it's a city, correct. Audio classification network says it's a city, correct. And so the multimodality network also says it's a city. Well, in the next frame, when somebody passes in front of the camera, the image classification network is certain that this is now the forest, because maybe it's confused and thinks that it can see trees or plants because of the shapes involved. But the audio classification network is still certain that it's a city, and so multimodality overcomes this by selecting the best class. Again, there's an example on the right where the audio was wrong. In both frames, this image classification network thinks it's a city. The audio classification network can hear the sounds of water in the background. I believe this is Las Vegas. But the multimodality network accounts for this error and classifies it as a city. So obviously the features that were extracted by the convolutional neural network were much more important than the ones that were extracted from the audio network, and vice versa for the first example. We then applied the trained network to totally unseen data, 2 minutes per class. And we can see here that the audio classification network performs really badly at 33.52%. The image classification network, it's okay, but it's not great at 65.92%. But then the multimodality is correct 856 times out of the total of 1071, which is 79.93%. So as we saw during training, even with unseen data now, the multimodality approach is still superior. Here's the error matrix for the unseen data normalized, and we can see that the 70% accuracy, the errors within that were from two main classes, which were the restaurant accidentally misclassified as the supermarket in many cases, and the classroom accidentally misclassified as a restaurant in about a third of the cases, just over a third of the cases even. And we conjecture that the big mistake, the restaurant as supermarket, well, visually we see a lot of people queuing up. Maybe we can hear a lot of people, and to the networks these get seen as very similar environments, so it makes the wrong decision. But if we take a look at the results without this restaurant as a supermarket mistake, it's a very, very robust network. So of course there's future work there to improve on making those kinds of mistakes in human environments. So to conclude, we found that image and audio classification are improved with multimodality. When it comes to all important unseen data, of course, when we go back to those examples of autonomous machines being part of the world, most of the data that they see is going to be unseen data, so robustness is very important. We found that for this problem, audio classification performs very poorly, image classification doesn't perform well, but with multimodality via late fusion, we still achieve a respectable result, especially when we consider that none of this data was present during any training exercises. So for future work, we want to directly compare this approach to temporal recurrent methods. So of course, they're much more computationally complex. So we want to see how this approach stands up to those approaches. We should probably better tune the image classification network, of course, because of hardware capabilities. We couldn't perform that evolutionary search like we did with the audio, but with better hardware in the future, we'll be able to do that. And then, of course, we can also physically go and test the algorithms outdoors with an autonomous machine. I'd like to thank you all for listening. The dataset is publicly available on my GitHub page, so feel free to perform experiments with the data or extend the dataset and see if you can improve the scores that we got. And you can also visit us at arvislab.io to see what we're currently working on. Thank you very much for listening. Thank you.